All right. Yeah, we are live now.
Nice.
That did take quite a bit of time after I pressed.
Yeah, I was worried.
I was wondering whether it's going to come back
on. I don't think I've started the presentation yet, have I? Shall I click start?
No, I don't see the presentation. So now, yeah. Let's see it now.
Yeah, there we go.
We give another minute.
Yeah, we'll wait one more minute and then we'll get started.
It's sunny, but there's absolutely no wind. Like everything is like standstill.
Right, it's 2 minutes past, so I think we'll get started then. So good afternoon, everyone, and thank you very much for joining us today for the 4th webinar in our Spotlight series. I hope everyone is keeping well during lockdown. So today's webinar is going to be about how the technology that LYTT uses to deploy our models as real-time solutions. So in previous webinars, we've spoken about the research and the development that goes into these models. And last week, we heard about how operators are using the results of our models to make decisions in the field. But in between this R&D that goes into the models and the end user eventually using the results, there's another part, and that is deploying these models as real-time solutions so that they're constantly working and continuously sending results to the end user. Just to quickly introduce myself, I'm James Ramsey and I'm a data scientist here at LYTT. I joined about 12 months ago. Most of my time here has been spent developing machine learning models. So I've worked on algorithms such as the water detection algorithm that you've probably heard mentioned in our previous webinars. More recently, I've become involved in the actual deployment of these models and I'm currently responsible for the development of LYTT's real-time software offering. Before LYTT, I worked as a reservoir engineer, and before that, I also worked for another distributed fiber optic sensing company. I'm also joined here by my colleague Vishnu.
Hello, everyone. I'm Vishnu Ramalingam. I'm a data engineer here at LYTT. So before joining LYTT, I was with the likes of Sony PlayStation, Betfair, Order Telefonica, and Orange Telecoms. And I was mostly doing ETL design and development, data warehouse design and development. So it's been like, what, eight months since I joined LYTT back in September 2019. And in that time, I've been just looking onto analytics software for the DAS and DTS stream processing, and also focusing on continuous integration and deployment into the cloud. I'm a part of a small team here at LYTT. It's myself, data engineer, and Enrique, our DevOps engineer, and Saumil, our security engineer, and Janti, our RTPU engineer. He's building the next generation LYTT RTPU. And of course, James, who's a product owner as well as the resident data scientist. Given the size of our team, on day one, we said we're going to reuse as much as possible and reinventing the wheel. So that's how we start off, and we built the real-time solution. Before we actually speak about the real-time solution, I would like to give a brief overview of what LYTT offers the oil and gas industry. That's from my perspective. I'm a non-oil and gas guy. This is the first attempt in oil and gas industry for myself. So LYTT is an analytics company, and we offer end-to-end solution, a cloud solution that helps petroleum engineers to see and understand what's going on in the well. By that, I mean what's being produced, whether it's oil, water, or liquid, anything, and how much it's being produced, and from which section of the well that's being produced. And all this in near real time. So how does how do we make this possible? Of course, you might have heard Pratt speak about all the proprietary algorithms. From my perspective, it's just light signals converted into acoustic and thermal signals by the DAS and DTS interrogators, which is then the algorithms run in the RTPU. And we extract some useful features out of it, ship into the LYTT cloud. And again, we enrich it with the machine learning models, like likes of James who have developed it. And then we just ship it back to the visualization system for the engineers to see it on the screen. So that's how we do it. And now I'll hand over to James to actually speak about the challenges we faced in developing this solution. Over to you, James.
Thank you, Vishnu. So before we go into too much detail, it's probably worth defining what we really mean by real-time analytics or real-time software, real-time solution. Well, for example, if we have water breakthrough in a well that LYTT is monitoring using DAS, so that well starts to start producing water, we want the results of our water detection algorithm, which says which section of the reservoir is producing that water. We want those results to appear on our visualization dashboard just 5 seconds later. And it's the job of the software to process the DAS data as soon as it's available and then send it onto the visualization dashboard as quickly as possible. And it needs to do all of this in a way that's scalable, robust, and easy to maintain. So easy to maintain goes without saying, really. We're a small team, and if we create something that we can't maintain, then we haven't done a very good job. It needs to be scalable because the number of wells that might be streaming DAS and DTS data to the LYTT cloud can change at any time. And our software needs to be able to quickly adapt to the amount of processing that's been asked of it. And lastly, it needs to be robust. We encounter a lot of difficulties with things such as streams dropping in and out, and our software needs to be able to handle this without crashing. Now, the points I made just there are probably true for any software analytics offering. So next, I want to talk about some of the challenges that are specific to our DAS real-time solution. And the first of these is what we just mentioned, getting data from the well to the visualization dashboard in just 5 seconds. So DAS data is really large. Even after we've applied our feature extraction, there's still a lot of it, and we're dealing with really high data rates. So processing all of this data quickly enough is a challenge in itself. And this is actually part of the reason why we need a scalable solution, so that we can easily throw enough computing power at the problem to solve it in the time that we need. Next up, the issue we face is that the connection between the asset and the cloud isn't always reliable. So in the case of oil and gas, the asset is going to be a platform. This could be offshore, somewhere like the North Sea, so quite a harsh environment. And we can easily lose connection between the platform and the cloud for, let's say, 24 hours. So the problem here is that when the connection comes back online, we've suddenly got 24 hours of DAS data all backed up, waiting to come through. Suddenly, we've got 24 hours of DAS feature data streaming to the cloud as quickly as the network will allow, and we need to very rapidly scale up our processing power so that all of this new data can be processed and we can catch back up with the real time. Conversely, when the stream's down and we're not needing to process as much data, we need to scale back our resources so we're not paying for any resources that we're not using. The other issue that comes when a connection suddenly reopens is that the data points tend to arrive all in one big dump, not in chronological order. So the streaming software is just trying to get data off the platform as quickly as possible, and it doesn't care which data is newest or oldest. Fortunately, each DAS and DTS data point is timestamped, and our model needs to be able to reorder the data as it arrives, and it does that. Finally, I've been speaking mostly about DAS so far, but of course we've also got DTS, and a lot of our models rely on a hybrid of DAS and DTS together. Now, the tricky bit here is that DAS and DTS are normally sampled at different time resolutions. So DAS data might be sent every second, whereas DTS might be every minute or every hour. And we need to combine those two data sets in a neat way so that it's a single data set that a machine learning model can easily process. So that's an overview of some of the challenges we face. And now Vishnu is going to explain exactly how it all works. So Vishnu, can you please tell us exactly what happens when a new DAS or a DTS file first arrives in the Light cloud.
James, before I can explain what happens to a file within the real-time software's journey, let's look at the architecture of a real-time software. So you see that dotted rectangle in the middle, and all the components within that are they form the real-time software. So we have three main bits to it. The first one is MongoDB. The second one is a group of microservices. To be precise, there's four. And the third one is an ActiveMQ message broker. So what does MongoDB do? So it keeps track of anything that's going on within the real-time software at runtime. And what does microservices do? So by the name, you can guess that microservices are things that they do specific things and only specific things. And what does the ActiveMQ do? ActiveMQ helps all these microservices talk to each other. So microservices, they don't talk to each other directly. They talk via the ActiveMQ messages. And all of these are open source solution. And when I said we wanted to reuse as much as possible than reinventing, and that is one of the reasons we went open source. Okay, now let's assume that a file comes in, and what happens to that file? The file is being shipped by the RTPU onto a file server or a cloud server location, and what happens to that file? If you remember, the first container microservice is scanner, and all it does is look for new files, and if it finds one, it just downloads it. And it also keeps track of all these new files that it downloads, so it doesn't download the same file again. And once it finds a new file and downloads it, it just drops a message onto the ActiveMQ so that the next service can come and find that message file. So that's what happens to a file at the beginning.
Okay, so we've got a nice long list of all the files on the file server, but when do we actually run these algorithms we've been talking about?
That's the next step, but it's actually a two-part step. The next microservice is a sampler service. And you remember the scanner has downloaded all the files and it provides the list of file names as messages in the ActiveMQ. Sampler just reads these messages and it knows what to do with it. When I say what it knows what to do with it, it does some pre-processing so that the algorithms can be applied. So what sort of pre-processing are we talking about? You remember James mentioned all these DAS, DTS, and hybrid models, which use both DAS and DTS data. They require different preparations. Some require 1 second worth of file, some require like a minute worth of data, some require like 1 hour worth of data, and all that sort of pre-processing. So that's what sampler does. So it prepares the data, and then it drops a message onto the MQ saying that, okay, I've prepared this data, and on to the next service we go. That's the predictor service. So now the predictor service is the one which actually runs the machine learning algorithms that James and his team develop. And so it has got the input as the pre-processed data. So all the predictor service has to do is apply the algorithm and produce the output. And it does nothing more than that. And also there's a cool feature within this predictor service that we have built in. James and his team, they can develop the algorithms independently. And once they're happy with the results and everything, all they have to do is just register the algorithms. By registering, I mean they have to give it a version number, they have to give it a name, and what sort of pre-processing the model requires, and also what data they require. As I said, some models might require both DAS and DTS, and some might require just DAS or DTS. And that's it. They register it, and the predictor service picks it up, and it knows which algorithm to apply on what prepared data. So it's pretty much delineated in that sense. So now we have the outputs produced by the predictor service. And what happens next? Obviously, we have to ship it to the visualization system so the petroleum engineer can see what's happening on his screen. And that's what the connector microservice does. So we can ship it to the visualization system, data lake, or external system if the client wants so. All this can be configured. And that's what the connector service does. And I hope that gives you a better idea of what's happening to a file within the real-time software, James.
Yeah, I think so. I think we all know now what happens when a new file arrives in the cloud. But one thing people might be wondering is, why do we need all these separate microservices and message brokers? Why can't we just run all the different parts as a single process?
That's actually a very good question. Uh, Let me just give an analogy. Probably let's think of a restaurant and a chef, given that I'm speaking to James Ramsey. Um, Suppose you own a restaurant and you want to serve customers. What we wouldn't do is there would be, I mean, you wouldn't be the only person working in the restaurant. If that's the case, then you would have to buy the produce, prepare it, cook it, and also serve the customers. That's not very efficient. So suddenly you have an influx of tourists. How do you serve them? So it's pretty much similar with microservices. So you have logical separation of things to do, like the scanner, just download new files, sampler, pre-processing, and predictor, apply the algorithms. How does this help? Um, you can just scale each individual bits on its own. Suppose prediction is what it takes a lot of processing power, then you can just scale the prediction. But if you had written this as one monolithic software, where reading the file, sampling it, predicting it, and sending it back, then you have to wait until one is over before you can start the next file. So that's where microservices helps very much. And since you asked about the microservice, I'd also like to just say what container does. You can see in the architecture diagram, each box has container in it. What we have done is containerized each of these components. What does that mean? So again, going back to a restaurant analogy, in a weekend, you come up with a new recipe at home, you cook it, you like it, and you want to just introduce that in your restaurant. So you go to a restaurant, cook it, and it tastes different. So we don't want that sort of surprises to happen. So whatever we develop, see the results in the development environment. When we release it to production, we want it to be exactly as we saw it in the development. So that's what container helps. So you just package everything, pre-package it, and all you do is just deploy that package in the production. So it would run exactly the way you saw it in development, and nothing changes. So no surprises in production. That's what container service helps us do. Over to you, James.
Yeah, thanks again for that. So what happens when something breaks? I'm guessing even the most reliable cloud services must go down every now and then.
Of course, yeah. We have seen it a few times now. And that's why we have MongoDB that helps us to maintain the state and also record what's going on in the real-time software. So if it does go down and we start everything back up, we start from where we left off the last time. So yeah, we did think about it, and MongoDB is our answer to that. So
Okay. Now, again, all of this does seem pretty complicated. How easy is it to actually deploy all of this? So, for example, if we had a new customer who wants this set up on their system, how easy is it to actually do?
I know it sounds too many moving parts, but it's actually pretty easy to deploy this. I mean, with all the softwares I've worked in my previous jobs, this is the easiest one that I had to deal with when it comes to deployment. So we use GitLab as our source code versioning system. And we also have few things as part of GitLab, like GitLab CI. This helps automated testing and building. When I say building, once you commit the code, you run the tests and test if they're successful. What GitLab does, it also has a feature to build. And by build, we build the containers. As you remember, the containers are pre-packaged ones. That's what we are going to deploy it into production. All this happens after we just commit the code, testing, building, and containers being built. So these containers are referred to as registry entries within GitLab itself. It has a private container registry, and we just jot that registry number within the Docker Compose file. And Docker is the container service we use. And if your target system, all it requires is Docker, and connection to this GitHub. We just have to run one command, which is docker compose up, and all your services are up and running. Of course, you need connectivity to your source system and also the target if you're going to post the results. If that's there, it's just as simple as running one command and everything is on. Back to James.
Brilliant. Thank you very much. Okay, so now we'd like to open things up for questions. So all you have to do is just enter any questions you might have into the chat that's part of this webinar. If you've entered those while we've been talking, that's also fine as well. We'll answer those too. If I jump forward a slide, there we are. Okay, so just before we start the questions, just want to let everyone know that we have another webinar a week today, so that's on the 28th of May, and also we have a paper being published in the SBE ATCE in later this year, so we will make sure to notify everyone when that becomes available. Okay, so just bear with us one moment while we take a look at the chat. Oh, right, someone's told us that our video images are obscuring part of the slide. Sorry for not not responding to that.
Do you want to pick this question, James?
Yeah, okay. Okay, we've got one question here. Can these processes be deployed locally as well as in the cloud? Okay, I'll take this one. So it's a good question, and the answer is yes, it can be deployed locally. Well, I'm talking about all of these microservices that Vishnu was just talking about. And we've actually been discussing this internally quite recently, actually. So for example, in certain countries, it's not possible to take data out of country. And in this case, it wouldn't be appropriate to send data to the cloud using the model that we've just discussed. So the good thing that Vishnu just mentioned about containers is you can deploy these processes anywhere, and that you can deploy them on different types of systems, and it won't create any issues. So one example of this would be to deploy these prediction algorithms on the RTPU itself. So that's the remote processing unit. So these features, obviously they're extracted on the RTPU, but we can then add all of the microservices which run the prediction algorithms themselves, so generate the flow logs, the SAN logs. And so this would mean that everything apart from the visualization is done on the RTPU before the data has even left the platform. So when you have that set up, you'd be able to send the processed final results straight from the RTPU to any secure location that you might want to. Vishnu, if you see a question. Oh, okay, good. Well, we've got another question. It's the same as that one, so I think we've answered two there, which is always good.
There is this question, I guess probably it's for you, James. Can you remind me how you reconcile the frequency differences in the DAS and DTS?
Yeah, okay, so I assume this is talking about the frequency that they're reported on, that the data comes in, not anything to do with acoustic frequency. So all of our DAS data we get once a second, and DTS data is typically sent once a minute or sometimes once an hour, depending on the system. We apply a sort of look back rolling average, so that at any point in time we're looking at one DAS, one set of DAS values and one set of DTS values, and the time averages that those two, the time periods that those two sets of data are averaged across may differ, but that's kind of the kind of things that we build in when we're training the models. It doesn't sound very complicated, but it's been a bit of a tricky one to program in to run automatically for sort of any arbitrary set of time, whether you're looking at per second, per minute, per hour for either DAS or DTS. But that's something we do have running now. So in the future, whatever models we build, whether they require DAS or DTS, and whatever sort of frequency of data comes in for either of them, we should be able to handle that quite easily now. Okay, let's take another question.
There is a question from Mahmoud, which asks, what format of DTS data are you looking for? I'm not sure about the format, but if it's just the file format that you're looking for, it's just CSV that we use. I'm not sure if that answers the question, but yeah, for both DAS and DTS.
And the same for DAS as well. What time range data do you use for the predictor? Again, I've kind of spoken to that, but it varies depending on whether it's DAS or DTS, and the model that we're using. It goes from per second to per minute to per hour. So I've got one here. How is each well's production data integrated into the evaluation analytics? Okay, so all of our models as an input only use DAS or DTS, so they don't use production data. One advantage of this for us is that if we're moving between different operators, we can guarantee that the DAS and the DTS are going to be in the same format. But the way that each operator keeps all their other time series data, whether it's choke values or oil production rate and stuff like that, is likely to differ a lot from operator to operator, and also where they store it might differ. So it would be problematic for us to rely too heavily on this kind of data. That said, we do use production data in the calibration stage. So each of our models, so that we can account for the subtle differences that occur from well to well, we don't immediately just plug them in and press play. There's a short calibration procedure that goes on before we're ready to deploy that model. So you've got to get that model ready for well A before you can deploy it. And for that process, we might use things such as the production data and the choke and so on to make sure that model's calibrated correctly before we deploy it.
There is a question about frequency bands of DAS. Do you want to pick that, James? It's like, do you auto pick the frequency bands of DAS for certain purpose signal detection?
No, we don't. We have spent a certain amount of time investigating what are the best features to extract from the DAS, because obviously no one's able to process raw DAS data. The amount of data is too large. So yes, everyone has to extract some amount of features. We're lucky to have a lot of laboratory data, so we can spend time investigating which frequency ranges, which acoustic features work best for us for the different predictive purposes we need. But once we've decided on those, they're relatively hard-coded. We are able to change them, but they're sort of fixed. So no, we don't auto-pick the frequency bands. I'm not entirely sure what auto-picking frequency bands might be, but it'd be interesting to hear. Question here, do you use different predictors depending on the fiber optic cable installation, permanent versus intervention? And the answer is yes, we definitely do use different algorithms from permanent to intervention. And we also use different algorithms from completion type to completion type. So open hole versus cased and perforated, and so on. They're all going to generate different types of acoustic signature. So we need a different model to be able to correctly recognize those. Okay, one large last question, I guess. We're running up on time a bit here. Raw DAS data is typically a relatively large file. Get out my way notification. When processed or binned by your analysis, how much are the file sizes reduced? We reduce it by an order of about 100, I think, but that's not a very accurate figure. It's something like that. Certainly it goes from a rate that would be impossible to stream to the cloud to a rate that we're able to stream perfectly capably. Okay. Vishnu, are there any other questions you particularly want to look at, or should we draw a line under it for that? Yep. Okay. Yeah, so we're up to half an hour now, so we'll stop that there. What we will do, though, is try and work through all of the questions. There are some still coming in now, and we've probably missed a few. It's been working up from the bottom. So we'll try to address those, whether it's in a blog post or something similar. We'll make sure we get round to answering all your questions. So on that note, thank you very, very much for tuning in. Hope you enjoyed that. I hope you found it informative, and we look forward to everyone joining us again, hopefully next week on the 28th of May.
Thank you. Have a good day.
Right, brilliant. Thank you, everyone. Bye.